Hi, everybody. Welcome to another C++ meetup. Today we have Sergei talking about the LFU cache. Thank you all for coming and take it away, Sergei.
Yeah, thanks everyone. Well, since it's C++ meetup, I decided we will do it old-fashioned with just a board. It should be a blackboard and a chalk, but well, we have what we have. Well, when I was preparing this talk, I was thinking that, all right, I can make slides and already start making those slides. I realized if I didn't know the topic, I would probably can't follow those slides because when you see some scheme of a data structure for the first time, it's not obvious what it does and how it does and where to look at. Slowly with time, you start to recognize certain patterns in those data structures. So they kind of similar in the most sense, but at first it's really hard to do it, and I was there also. So at certain point, I realized that probably the best like way to describe something is to draw it by hand. It could be not perfect, but it works. All right. So today topic is LFU cache, and let's begin with why we need to even like discuss that. So, well, even we humans, we do use cache. So, for example, if you're worker in some pharmacy store and some clients comes to you and ask if you have something like a painkiller or something against the flu or something, I know, vitamins. You don't need to check the database like every time. You probably already know that certain things are very, very popular, and you know if you have them in stock and what are those parameters of the certain good and whatnot. So it's basically you use cache. And obviously, why do we need a database if we have cache? The problem is like you can't store everything in cache because it defeats the whole purpose. Cache start to be a database, not only like physically but also mathematically. It's like the idea of cache that you store not everything. And since you store not everything, obvious and natural question, how to decide what to store. And here you have such thing like cache eviction policy. So it's some rules which you use, what should go out of your cache when you reach your capacity, and what should be inserted instead. So there is multiple ways how you can do that. LFU one of them, but more popular probably LRU, sometimes with an S. It means for segmental, and LRU is least recently used. LFU stands for least frequently used. So one letter difference and so many differences you will see later. And there is many others approaches. Some of them could be hybrid of those. Some of them could based on something else. Could be something as easy as random. So, for example, you have capacity of 10. You have number like item 11, and you just decide, okay, any can go, and we place it instead. But sometimes it's efficient, sometimes it's not. So to explain LFU, I will start with reminding you what is LRU. So let's imagine our client, and our client goes to our database. And we have our cache, which will be like this. We go to cache first, and if we can't find anything, we go to the database. So like with cache, we don't go to the base directly. So for example, our cache has capacity of, let's say, 3. So this is our cache. First of all, what data could be there? It could be some strings, could be some metadata, could be some images, everything. So we already need to decide that we need to hash our data just because we can't store an image as a key. So we already see restrictions that we need some hash function, which we can use different hash functions, as you know. And let's consider an example. We have some values which come to our database. Let's say 2, 3, 1, say, I don't know, 5, and let's say something repeats. If we do list recent, list recently used strategy in time, what we do. So for example, first we have 2, we put it into our cache. Then we have 3. I will redraw it in a timeline so it would be easier to understand. Then we have 1. And we reach the capacity. So after that, we have to remove something. And here's the question. What do we remove? When we use strategy of recency, it's in a sense it's easier because we evict an element which was least recent. So in our case, it's 2. We have to remove 2 in this case. And let's say we put 5 here, 3 and 1 stays here. When we get 3, we don't need to do anything because 3 is already here. Maybe we should update something, but we will talk about it. So, as you already can guess, it's not the most efficient strategy. Why? Because first of all, we need to find an element in our structure. While, okay, by the key, in the hash table, we can find an element in a constant time. The problem is like how to update the structure because it's seemingly random. And we actually need to find a way to efficiently evict an element because we don't know which one we should evict. So we know which element we add. In this case, it was 5. But we don't know which element to evict because we need to know somehow which element was the first in our history. So there is how many containers do you know, like types? Actually, it would be either vector. We can have something like linked list. Double linked list, not that important. We can have a tree. And we can have a heap. We can also have a graph, but not today. So if we use vector strategy, and we want to know which element is the least of some metric in our vector, it's a full scan. Or we can keep it sorted, but in the worst case, it's still like a full scan. So vector doesn't work for us. Linked list, we are lucky. It's the best strategy. Why? Because we can keep it sorted, and we know that if we have, in this case, already sorted by time linked list, it would be 2, 3, and 1. And we need to evict an element. It's always the first element. And next, we need to insert our new element. And it will be in the start. So we remove this one and put this one. So we don't do anything. Okay, in this case, when we have repeated element, what we do? We see, okay, we should not evict anything, but we have a hash table of pointers, so we can go to this list from our, some hash tables. But this is the element we're looking for. And what we need to do, we just need to modify this linked list to 1, 5, and 3. The thing is, we just evict this element from here and insert it in the start. So it's basically free operation in the linked list. But in a vector, it would be obviously a restructure of the whole vector. All right, 2 interesting containers here. We can have maybe not an optimal solution, but if we need some other properties, it might be the case that they are good for us. But we already found the best solution for our current problem. Great. So what we need to know that if you need to implement LRU and you don't know anything else, you just need linked list. That's it. Linked list works for you. So we can talk a lot about LRU, but the topic is LFU. So what's the difference? Right now we count not when element was put into the history, let's put it that way. And here we have thing like a time. The problem with frequency is that we lose this linearity. So our linked list doesn't really work because here you always evict from the left, you always put to the right, and you just have basically read-only pointers into the structure. That's it. But right now you don't know not only where to get the element, which you knew from the hash table, but you don't know where to put this element after. So for example, here you have frequency 1, you have frequency 1, frequency 1, and frequency 1. And when 3 comes the second time, it could be here, it could be there, we didn't know, because it could be 2. We need to scan the whole structure, and it become, unfortunately, not constant. We need to full scan the whole linked list. So for obvious reasons, vector doesn't work for us, linked list doesn't work for us. There is 2 more containers. Let's consider tree. What can we do with tree? I need to probably need a second page. So let's repeat. A few. So what can we do? We need to keep structure which is sorted by frequency. At the same time, this structure should be pointed by elements from the hash table, which is our cache. Well, in the case of a tree, we just need something which can be sorted. In our case, it would be frequency, and we are good to go. So for example, in our original case, it was 3, 2, 5, 1. I deliberately did different order. So, first of all, let's see how it works right now. So again, we have capacity of 3, we get 3, and we need to store frequency 1. We have 3, 2, and we still have frequency 1, 1. We have 5, 2, 3. We have 1. In this case, we can evict any of those. Let's say we evict the last one. Doesn't matter. So we still have 5, 2, 1. All frequencies are ones. And when we have 3, this is the problem. You see? It should be frequency 2, and we should store it, but we lost it. This is why LFU is not that easy. So not only you don't have the linearity of time here, instead of time you have another metric, which is frequency. You also can't have the structure perfect, because it can happen on any capacity. So in this case, yeah, you remove something, and your structure would be 3, 5, let's say 1, doesn't really matter, and you have frequencies 1, 1, 1. But if you were not that unlucky, it could be 2. So 2 or 1. One of the ways how you can solve this problem is that you can store keys and frequencies more than you really store the data. So you have already 2 capacities. The capacity of so-called metadata, which is in our case our keys and frequencies, and the data which is really in your cache, which takes more memory usually. And let's say you have like last 1,000 elements which are stored completely, and last 1,000,000 elements or 100,000 which are stored only by keys and frequencies because it's cheap. But we will not consider this case. It's just very nice to have in mind. Another problem which you can face on big numbers, let's say instead of numbers, you have URLs. And let's say you have a website and you have some styles, some images, maybe some videos. You have multiple pages. But for example, one of those pages are very popular. And it can be popular till the end of times, and it's great. You keep it always on the top. It's always in cache, fast, great. But it could be that you want to update your pages, and they can reshuffle by popularity or something. And what is not really important to you now will stay in cache for a very, very long time, and your cache will degrade in terms of you have a lot of elements which you don't really use right now, but they kind of deserved their place on the top in the past. So you can see also this abbreviation, LFUDA, which stands for dynamic, I don't remember, let's say adjustment. So we can have certain strategy which will reduce frequencies in a time or by some metric. So for example, if we deployed our new site, it would be a waste to throw away the whole cache. But we can say, okay, since we have a new deployment and those artifacts might be needed by users who did not updated their site yet, you can reduce all those frequencies to some number, or you can divide it by 10, or you can do whatever, basically. It's also very nice to have it in mind. Now, let's consider our like tree structure, which we discussed, because there is multiple ways how you can do that. So, for example, if we do just a tree, it's basically goal to approach. You have a sorted tree, sort of balanced. The problem here will be that you will have advantage on big numbers, and you have in a normal binary tree or search tree, you have a lot of pointers, which would be a waste on current architecture. So it's recommended to use B tree. In the case of B tree, instead of have one element in one node, as you know, you have multiple elements, and they have pointers, multiple pointers to other similar structures. This is B tree. And this is just the tree. All right. Would it be fast? Yes, it will be as fast as you can get when you do like non-probabilistic, no tricks, nothing, just normal LFU. And here you have multiple choices how you do your keys. So for example, you can store in a B tree your frequency. You store your key, and you store your value. And frequency is your key in a B tree to be sorted. And key value is just basically your metadata to have ability to, I don't know if it can do that. To have ability to have a pointer to your hash table, where you just have key values, key and values. Instead of value, you obviously have this value by pointer. And key could be just key, or could be pointer, depending what you need. Maybe sometimes you just need to full scan your cache, and it's easier to just full scan a B tree, and you don't need to know like pointers and go to another data storage. You can just know your keys, and by key you can find an element at the any time. Or you can store it as a pointer to a hash table. Not that important. The main important thing, you just have your sorting key by frequencies, and when frequency updates, worst case is logarithm to evict and logarithm to insert. Everyone is happy. Great. But most of the time you just move it around one node. Interesting case is when you want to make it really, really fast, and it appears that B tree is not the fastest. Like mathematically, they would be the same, and you already probably guessed that I'm talking about heap. Why heap will be faster? Any ideas? Yes, exactly. We probably forgot, but we are on C++ meetup, and what we care most is cache locality, right? So how we can do heap in this situation? Actually, pretty much the same way. The only difference that you are not obligated to store it kind of together. While in the tree, it doesn't really make sense to store it separately, because you will have just fat nodes in terms of you have like 3 separate vectors which we use as a node, but we kind of have no advantage because we have still a lot of jumps in those pointers. But in heap, you can really have advantage of implementation where you have heap for just frequencies and just two mimicking ghost vectors of keys and values. And this will be real heap with like indexes 0, 1, so on. And you have kind of virtual pointers which are not existent. You just know that 0 points to 1, 1 points to 2, and so on. And plus you have 1 points to 3, 2 points to 4 and 5, and so on. Just normal stuff, normal heap. And you just need to mimic key and value because they are not a heap, obviously. It's just seemingly random vector of keys. Key 0, key 1, so on, key n. And same with values if you need them. If you don't, maybe you don't need them. So you can actually not have this and have just key value storage, and all you need just heap and a list of keys. So now, why do you have cache locality? First of all, actually B-tree also uses cache locality, but not that great. Here you can store a lot of elements which will be forward from your traversal. And some of those jumps would be completely free because you have them in your cache. And the only hassle you have to have is that you need to mimic all your manipulations with the heap on a ghost vector, which does not know anything about your structure. And you have to, because of that, you have to re-implement maybe this one customly because you need to have this ghost vector. But probably there are libraries which already do this with some template magic. All right. That's all I've got. And obviously benchmarks. If you don't know like what keynotes or topic to discuss, always discuss benchmarks, always work. And let's see what we have here. There are two implementations in C++, and in each language implementation, like, oh, there is an artifact, doesn't matter. So there's two graphs. It's implementation in Rust. This is implementation in C++. It appears the structure is the same. As you can see, here it goes like this. Here it goes like this. And what does it show us? First of all, it's log scale graph. So here you have implementation with tree, which is B-tree, with sorted vector, where you keep it sorted, with indexed heap, which we discussed in the later, and so-called bucketed linked list. We didn't discuss that because it's the worst. I decided to skip it. It's not that important. The idea was that for each frequency, you have a bucket and you put multiple elements to that. But if you have seemingly random nature of your data, it doesn't help. So you may feel that, okay, if frequency bumps by 1 every time, I don't need to move a lot of pointers, especially if you have separate buckets for separate frequencies, not like you have 1, 1, 1, 1, 1, 2, 2, 2, 3, 3, you have just 1, 2, 3, and inside you have multiple elements, still doesn't help. So as you can see, indexed heap grows as well as index tree, but a little bit faster, just because of this cache locality. So this repo is open source on this link. So if you will find any bugs or suggestions, or maybe you have your implementation and you want to contest it against, I didn't try to make it super fast. It was mostly for like mathematical reasons and theoretical, not like for squeeze water from the stone. So as you can see, at least for me, it's predictable what should happen with the numbers. Now that's it. That's all I've got.
Thank you for the presentation. So I have a question because I haven't heard about LFU at all like before, and where is what is the case when LFU is better than LRU? Because LRU usually like it's easily to find, but LFU is more sophisticated in this case.
It appears that none of them separately is the best solution for the real world. Usually you want to have some kind of a mixture of both approaches. So basically, and not only those two, you usually have multiple approaches. So you can have LRU, but with an S. It's segmented. Usually you have two segments, like let's say the best and the candidates. It could have multiple names. So the idea is like the best is that you want to keep always, and those you can select by frequency. And candidates, you can select them by recency. So that way you don't have to store a lot of frequencies, because you can have like everything is 1 except maybe 10 elements have like millions of frequencies. So you want to have those millions in a separate like privileged bucket or segment, but you also need to have a mechanism to promote someone to privileged and demote if you realize that some of those is not really used. Let's say you deploy it a new website, it has different design, and you need to redo the whole cache and reworm it, and yeah. So usually, and plus you usually have something like probabilistic. So if you really work in very high load thing which need to have certain cache parameters, and only you know the nature of your data and specificities of this and intricacies, you can make a mixture of multiple approaches. So usually in the real world, you do like combo of LFU and LRU.
Hi. So it was a throwback to some 10 years ago when I worked on software that was implementing supply tree for that. So if you're familiar with that strategy, that might be interesting for everyone involved. I don't remember exact details anymore.
Let's talk about supply trees. Let's see how many people will be asleep in the end of the presentation. Yeah, actually, I'm joking. It's a very nice topic. It's a little bit hard, but it's fun.
Thank you for this nice talk. I will not have a very substantive question because I missed the first half. But still, I want to see how results differ between C++ and Rust. And the second question, if you can go a little bit up Yeah, you see, if this repository is just containing your implementation of this, why is Rust used so much more?
Because I wrote benchmark also in Rust. So it's roughly actually the same. Well, maybe C++ was a little bit more concise, like some random 2 or 3%, but most of it is benchmark. Also, you can ask why Python is here and Starlark.
The speed.
And the speeds are basically the same. Rust is a little bit slower, but I challenge you to find those 3 pixels which they are different. If I just change those 2 graphs, you will not find the difference. It's actually very interesting then that in C++ you have some jumps here. In Rust it's a little bit more even, but well, they both LLVM, so it's both C-lang underneath.
So you're saying if this is a GCC, maybe it's better.
Maybe. PRs are welcome. The point why I did 2 implementations in Rust and in C++ actually was also to prove in the sense that mathematics works the same way everywhere. And as you can see, graphs are similar, which proves that, well, on small numbers, you can kind of do your shenanigans with like cache locality and everything, but in the end of the day, you can't beat asymptotic. And yeah, it's really hard to see that in terms of its log scale. So when you see like just a linear line, it's actually not great.
Okay. Anybody else? Oh, thank you, Sergey. And that concludes the official stuff.